At the end of 2018, we told you about very exciting data coming from the LHC experiment at CERN. Data that could change our vision about the universe and how it works. Data that fueled discussions, enthusiasm, and ideas in the physics community. How did that adventure end, if at all? This is a story of enduring promise, but also of some disappointment, which illustrates well how the work of those who seek to unlock nature's secrets is carried out, and what they think about the open questions in physics. Let's start from the beginning. The whole story starts near Geneva, where CERN is based, the international laboratory hosting the largest particle accelerator ever built, the LHC. Inside the LHC, beams of protons move at light speed in opposite directions, colliding at specific points. As a consequence, new particles are created and decay, producing traces that are recorded by huge detectors. These traces provide very useful information about the basic components of the universe and of the forces through which they interact. Physicists were particularly intrigued by the results coming from one of the 4 huge detectors related to LHC, known as LHC-B. To understand what exactly has shown up, we have to have a look into the detector where, after colliding, protons annihilated, producing different particles. Among them, so-called B mesons, containing elementary particles called B quarks. B quarks are the main players in our story. Almost immediately, they decay, transforming themselves into other particles. For instance, in S quarks and pairs of other particles. These pairs of other particles can be of 3 different kinds. One pair is formed by 1 electron and 1 anti-electron. One pair is formed by 1 muon and 1 anti-muon. And one by 1 tau and 1 anti-tau. LHCb can detect well 2 of these pairs: electrons and anti-electrons, and muons and anti-muons. Physicists would have expected these 2 pairs to show up with the same frequency. Instead, one of them, the muons pair, seemed to be rarer than the electrons pair. But B mesons can also decay in a different way, producing C quarks and pairs of other particles of 3 different kinds: muons and neutrinos, and taus and neutrinos. While according to the theories, also these 2 pairs should have shown up with the same frequency. Once again, the pair taus and neutrinos seem to be more frequent than the other pair. These 2 anomalies, the suppression of muons pairs and the enhancement of tau and neutrino pairs, led to a lot of speculation among physicists.
According to the standard model, these particles interact at the microscopic level via 3 fundamental forces. We have the strong force, which acts on all the quarks, and actually is what, for instance, keep up and down quark to form, in a bound state to form the proton. And then we have the electromagnetic force, which act on the quarks and also on the electron, the muon, the tau, and is responsible, for instance, for electricity. And finally, we have the weak force, which actually is felt by all the 12 particles. What is particularly important is that these three families interact via the forces exactly in the same manner. So the electron, the muon, the tau are, in a sense, identical copies from the point of view of the standard model, except for the fact that they differ in mass. So if you can think of the muon as a heavy copy of the electron, the tau as an even heavier copy of the muon and the electron. And the same is true for all the particles in the different families.
The standard model has made many predictions, which have been successfully tested in several experiments. The last of these successes was the discovery of the Higgs boson, announced in 2012.
The observation of the Higgs boson was a great success. It was the last application of the theory which is necessary in order to confirm the standard model. However, still the standard model is not fully satisfactory, since there are observations which it doesn't fully explain. For example, the nature of dark matter. Its existence we confirm only through indirect cosmological observations, and we were not able to observe it directly so far. Another example of the puzzle which is not taken into account by the standard model is why various elementary particles have such a different mass.
So now physicists need to move forward, finding solutions to the unanswered questions. And there is a terrible lack of hints, of glimpses coming from the experiments that could show interesting directions for future research.
Usually, physics research is like a tennis match between us, the experimentalist, and the theorist. Sometimes the theorists formulate hypotheses that we need to check with an experiment. Sometimes it's the other way around. We submit to theorists some surprising results, then they formulate hypotheses, and then the ball is back to us that we have to find new methods, new experiments to check their hypotheses. But we always need a starting point.
The anomalies observed at LHCb created great excitement exactly because they could, and still eventually can, be the starting point that physicists were looking for.
The reason why we are very interested in these anomalies is because they seem to signal the presence of a new fundamental force, a force that should be very different from the known forces present in the standard model, a force that should act differently on the particle of the different family, should be a force that should act somehow stronger on particle of the first family, much weaker on particle of the second family, and super weak on particle of the first family, contrary to what all these other forces do, which on the other hand do not distinguish the different families. So if these phenomena were confirmed, this would be a major discovery.
Yes, but what happened? Physicists declare to have discovered something only when it has shown up so many times that the probability it is a false positive is less than 1 in 3.5 million.
For either of the anomalies, we didn't reach a confidence high enough to claim a discovery. In general, when you do that analysis, there is not a standard method, but there could be several methods because it's kind of an art form. In the case of the anomaly of muon versus electrons, for instance, we had two methods, and unfortunately these two methods did not lead to the same results. This was of course disappointing, but this gave us hint to develop a better and more precise method. This new analysis, however, did not strengthen the anomalies, but it weakened it. This doesn't mean that the effect cannot be there, but if the effect is there, it's much smaller and much more difficult to observe.
What happened has been disappointing, but not completely surprising. Listen to what physicists were saying years ago.
To be really honest, I would not be completely surprised if some of them fade away.
It depends on the model. There are certain models where I think you can have even 10-15% in RD star.
If an anomaly due to the excess of electrons versus muons would be confirmed, even if smaller than hypothesized, it would still imply the existence of a new force of nature. But the point is that physicists will need much more time to have a final answer. However, not all the anomalies have disappeared. The second one, the enhancement of tau and neutrino pairs, is still there.
New analyses of decays of B mesons to tau leptons have also been performed. However, they have not significantly clarified the situation. The effect can be large, but we are still far from claiming a discovery at the moment. The reason for this is that these measurements are very difficult, and therefore more data and more experimental techniques are necessary in order to progress further in this understanding. Luckily, right now, LHCb is collecting large amounts of data which can be available in the next years and which can be used in order to improve our understanding of tau leptons. Furthermore, LHCb is not alone in this exploration, as there are other experiments at CERN which can help with complementary measurements. And finally, there is also an experiment in Japan, BEL2, which can provide new information about the B decays with tau leptons.
What physicists are facing is still a long road. As for every road leading to the unknown, nobody knows if this will lead to a major discovery or if only dust will remain. But one thing is clear: the journey is worth to be undertaken.
Even if all the anomalies detected by LHCb would vanish upon further data analysis, thinking of how we could explain them has been very beneficial. This is what has led us to consider a new type of fundamental forces, a type of forces that were never considered before. And now we realize that these theoretical ideas are extremely interesting. They could lead us to the explanation of new open questions, such as the origin of particle masses, which are very important. These are very important open questions, somehow related to the anomalies of LHCb. So this is an extremely interesting theoretical exploration which has started. When entering into a new territory, when performing a new type of experimental exploration, a discovery is never guaranteed. However, already by walking in this new territory is what can show new direction, is what can lead us to new idea. This is really how progress works.
Time will be needed to know the real end of the story of the anomalies initially detected at LHCb. It might be a few years. In the case the analysis at CERN confirms at least the enhancement of taus in the decays of B quarks, or if the experiment BEL2 in Japan observes related anomalies. But it is also possible that the traces of the existence of further fundamental forces are out of reach of the experiments now available to physicists. In this case, they, all of us, will have to wait for a more powerful instrument. An instrument such as the Future Circular Collider, FCC. This is a huge particle accelerator, about 90 kilometers in circumference, that physicists are considering building at CERN when LHC will have finished its operating life. Waiting for the FCC would mean waiting for at least 20 years, but the FCC would represent a change of perspective in the way we look at the universe. A big step that is definitely worth taking, because only challenging our current understanding of nature's laws do we have a chance to make progress.